So today's lecture doesn't have a working tablet. It's terrifying. Music is a bit glaring. My apologies. Is that better? I'll bring you over here. Strang's introduction to linear algebra and Axel's linear algebra done right are also solid choices. Former matrix focused, latter is more vector space focused. Okay. So yeah, that was part of my... Who would have taught me this? This would have been taught by a geometer. So put that spin on whatever you need it for. Okay, so am I recording before I do this? There's nothing worse than yes. I have way too many things open. So we are on lecture 3. And this one I'm calling Solving Linear Systems. So the motivation that we're going to work through with this one is coming from a place of what we possibly will have seen in school with simultaneous equations, and I'm going to try and keep things very graphical as much as I can for that nice geometric interpretation. And then we're going to build up to the why it's in a matrix and why we didn't spend ages doing matrices, and also general methods that could be used for general systems. So moving away from that 2D, 3D, if we did have an n-dimensional system of equations, what is the process by which we could solve those? There's going to be a few points in this one where I'm going to stop and make a conscious choice to disregard something, which might feel like an obvious cat, why aren't you doing this other thing? And that is because that's next week's lecture. Stop being keen beans, and we'll talk about it then. So yeah, there's a specific point where I am specifically not introducing matrix inverses. So for those of you that know what that is and are mentally preparing for it, disregard it. That's not this time. Okay. So equations describe... Ooh, I cannot see my corner of the screen. Sorry. I do this thing where I put the projection of the screen in the corner so that I don't write like underneath the... That's way far out. Close enough. There we go. So I don't end up writing underneath the thing. So that was an absolute nightmare when I did the mechanics course, was writing underneath the webcam. So equations, this is going to get quite esoteric. Equations describe a collection of values that satisfy some sort of relationship, just as a refresher. So there's a relationship or rule that solutions obey. So that might be, for example, y equals 2x is an equation where for every value of x, y is twice that value. And that's a really like simple equation. Can I turn my volume up? Cap. Okay. I appreciate that I do kind of stream quite quietly and I am facing like this way away from the microphone, but hopefully it's not too bad. What I could do, which would cause chaos, is try and find the mic stand. Okay. So y equals 2x, really simple equation. Generally speaking, has the form y is f of x, where f is some function. And that can be really simple, like just multiply the thing by 2, or it can be super complicated. And this is where, when we teach equations in schools, we sometimes think of them as like machines. So you put in a value and you get out a value at the other side, and it's a series of operations that you do to your input. And this might be like, Kat, this is really beginner stuff, but I really want to start from basics. So we have our input, we have our function, and we have our output. So visually, we represent this on a graph. So we represent this graphically, where we have values of x, and then values of y, and then f of x might be some function here, f of x. And that's a really complicated relationship. This one's a bit gross, but something a bit more simple, like y is equals to x, might be just be this straight line here, f2 of x. And some of them are more simple than the others. Linear equations, because we're talking about linear algebra in this mini-series, so we want to keep to linear equations. Linear equations linear equations are ones for which the variables have power at most 1. And here I'm using variables as inputs. Have powers at most 1. And variables not multiplied together. So that means that everything has a linear relationship. Okay, so up here we have the relationship y equals x is linear, but y equals like kx file minus x to the 5 is not linear. And that's because of these powers that are making it, technically this equation is quintic. Just as a language lesson, you've got x to the 1 is linear, x to the 2 is quadratic, and this is specifically highest power in the equation. X cubed is cubic, x4 is quartic, x to the 5 is quintic. I have no idea about the spelling on these. I think that's right. But we're all possibly familiar with a quadratic equation. We're very happy with it. And it has the form like a nice parabola shape. Cubics then have this curvy shape to them. Quartics have maybe something more funky going on. Quintics again have even more funkiness going on. And that means that our linear equations are straight lines. Okay? As we get more and more powers, you get more and more funky bends and interesting stuff happening. These are not the trivial quartic and quintic equations I appreciate, but they are themselves quartic and quintic. this is the really long way of saying that linear equations describe straight lines. And our alpha from y is a1 x1 plus a2 x2 plus a3 x3 plus an xn. So that is where your xi are your variables and your ai's are constant coefficients, and these will be sort of, let's call them real numbers for now. But we might have like y is 3x1 plus 2x2. Equally, we could have x, y, z as our variables. Our variables can be whatever, you know, equivalent axes we want them to be. This is like a general n-dimensional equation. Technically this should be, okay. If we're being truly general, then we set it equal to constant on the other side as well. And then normally we'd write it the other way around. We don't tend to write y equals and then a bunch of stuff. So that's our sort of linear equation. I'm going to bring chat up a little bit so I can see what y'all are saying. Who's my top 3 mathematicians of all time? On a metric that I'm not disclosing, because I can't be bothered to think about it, my supervisor, the problem is all of the academics all the mathematicians that I think are really cool, that have done really cool stuff, are probably assholes. So I'm like trying to just check. Let's put Ada Lovelace up there, because absolute baller. And then either Lord Rayleigh or von Neumann. Like, I think he is a prat, but just the amount of stuff that he did was incredible. Kat does maths, Hannah Fry, my maths teacher. Aww. Gauss and Euler were alright, that's fair. Let's just do a quick sanity check on what on earth von Neumann got up to. Like, I highly recommend looking at his wiki page because it's just the most insane. Okay, there's nothing immediately on his wiki page that's like problematic conflicts. So, I mean, aside from all of the defense work, yeah. Von Neumann is my actual like famous mathematicians from history answer. Ada Lovelace as well, and then yeah, Paul Milewski is just like, he's one of the best mathematicians I know because he taught me. Okay. Yeah, he did a lot of stuff, Cap. That's what I'm saying. Alice Roth, inventor of Swiss cheese. Yeah, well, I Google Alice Roth, I get a baseball player. Yeesh. Okay, let's get back into it. thank you for the follow. Welcome in. Okay, so we have our general form of a linear equation, but it's made up of terms that have a, x to 1 or the 0. Where this is sort of our constant, and this is either a linear variable, i.e. it's just x, or x to the 0, which is always going to be 1. So at which point that term would be a variable, would be a constant. Jumping back to 2D, the general linear equation is a straight line. So we could write it ax1 plus bx2 equals c, but more often than not, but perhaps more familiarly, we write our y equals mx plus c. Okay, and we get from one to the other by setting x1 is x, x2 is y, and then, I need to do some things in my brain. That's x1, that's x2, that is going to be b over a, and that is now c over a. So we can rearrange the equation, and technically minus b over a, from one to the other by just doing a change of variables, this is called. From our x1, x2 to y1, x and y even, x and y. Assuming a is non-zero, yes. In fact, assuming all of these are non-zero terms, because otherwise that's a really boring general system of equations. But yeah, specifically if we're dividing by something, a is non-zero. Okay, and the reason that we write it in this way is because it's really nice for describing what's going on graphically. So x and y. What's wrong with c equals to 0? It's just boring, isn't it? So that's our line y is mx plus c. And what we say is that c is called our y-intercept. It's where the line crosses the y-axis. It's the value that the line crosses the y-axis. And our m is our gradient. Specifically, c is the value that y takes when x is equal to 0. C equals to 0 is the interesting case. All the other ones are just translates. This is not wrong. But for generalization, we're not solving homogeneous equations yet. So that's the equation of a straight line. And hopefully that's something that is quite familiar. And you might be like, again, why am I doing this? Well, remember what I said about equations being rules. What this equation is saying is that for every value of x, if I multiply it by m, add c, I get a value of y. And we can have a long conversation about domains and ranges and codomains and all that jazz, but for now, just let's keep it abstract. Equally, I could say that the line contains pairs of points which satisfy the equation. So, or coordinates of points, not pairs. Pairs of coordinates which describe a point, which satisfies the equation. And I have written it down so I can copy it instead of rambling. So every point on the line is described by pair xy which satisfy the equation. So a line can be thought of as like an infinite collection of points. Okay, which are described by these xy coordinates. So that's why whenever I take a single value of x, I combine a single value of y, and I get out my values. I can do this again in R3. So let's like add a dimension in. So in R3, a linear equation for, let's do x, y, z to keep it nice and simple, is of the form, and again I could set c equals 0, but I'm not going to. Instead I'm going to do ax plus by plus c. And that now, instead of describing a line, thank you for the follow, welcome in. Am I reading your username properly? Yeah, I love it. Welcome. Okay, so this doesn't describe a line because now we have two x and y coordinates, or we have an x and a y coordinate and a z coordinate. So this now describes a plane. So I could do sort of plots of this where I take x and z and I look at it and I would get a line. I could do x and y, look at it, I get a line. I could do y and z and look at it and get a line. But generally speaking, this is where my very bad drawing comes in. I do apologize. I'm very impressed that went through. We now get something that sort of looks like an infinite dimensional rectangle. So it doesn't have edges like I've drawn, but it's like a fat plane. But if you think of it as just like a slice through space, okay? One really thin flat sheet, plane described by z is ax plus by plus c. So it's a flat sheet. So if I'm on that plane, I'm walking around and it's all flat. If I'm looking, say I like look down the z-axis on it, and I have xy, what I'm seeing is like all of it. Okay? If I were to look at it through a specific side angle, don't know why it's looking that way. I suppose if I looked at it through any angle, I would see all of it, but you know. You know what, actually, let me get Desmos up, because why make life harder when I could make... There we go. Apologies for the thing. So let's do 2x plus 3y. And that's a plane in space, plus 6, and we shift it. So we can look at this and we get this sort of infinite flat sheet, which if I look precisely on is just a straight line. if I look top down and it's sort of expanded out forever, it would keep going and fill this space. But it's a sheet. So setting things to 0, if I just do z is 3y plus 6, we get rid of any change in x. So if I look at it in x, it's all constant along this axis. Oh my god, you can spin these things. That's so fun. If I do the same thing in x, now it just looks like a flat plane in the y direction. And again, it's the thing. So we end up adding in this like rotation whenever we shift things by y. So y, 2y, 3y, 4y, 5y, 6y, and so on and so off. And then shifting things again goes away from the origin. So you can see that it's this z-intercept now. It crosses the z-axis at a value of 6. So that's our 3D linear equation. If I do things and I make this nonlinear, I get way more complicated shapes going on. And we don't want to deal with that. But if we set z to 0, the equation that we get is just 3x minus 7y equals 6, plus 6 equals. We get our straight line, and then we're back to 2D coordinates. And you can extend this to 3D vertically, and so on and so forth. So, God, that really is an awful drawing, isn't it? I think it's kind of interesting to note that the shape of an r to the n equation solution is r to the n minus 1. So what do I mean by that? 2D equation has line, which is a 1D as its solution space. 3D equation has a plane. I am glossing over a lot of like very rigorous stuff when I am saying this, so don't come for me. But plane is 2D space. And then so on and so forth. So the 4D equation would have 3D space. And it suddenly gets really hard to visualize and to understand what's going on. But that's the contained set of solutions makes up an n-1 dimensional space. Which is useful for like visualization purposes as well. But we're going to stick mostly in our like nice 2D, 3D little domain for now. So sometimes though, we need to impose more than one rule. And what that means is we need to impose more than one equation. Okay, so what does that look like? Well, let's take the equations 2y plus 3x equals 4 and x minus y equals 7. I'll call them equation 1 and equation 2. So solving both of these systems, or solving both of these rules, it means I'm looking for a pair of values which satisfy both of them. I want a value of x and a value of y, a corresponding value of y, which is both of these relationships. And this is where sort of simultaneous equations has come from, is trying to solve this. And what this looks like is if both of these are equations for straight lines, and I am probably not going to end up drawing these properly. It's going to be like there and there. So that's 1 and that's 2. Then this, if each line contains an infinite set of points, the points that are solving both of these, or in both sets, is precisely where they intersect. So solving both equations is equivalent to asking where the lines intersect. Okay? So this was the bit in school, I think, that for me really helped me sort of understand what was going on with algebra, because like I can see it very visually, like do these things intersect? If they do, how often? And when you do simultaneous equations at A level, so in the in Wales at 16 to 18, we started doing non-linear systems of equations. So maybe one of these was quadratic, and we had to look for like equations that, you know, where do two equations for circles intersect at most? 0, 1, 2. Drawing it out really, really helped. But yeah, essentially, when you solve systems of equations, what you're asking for is where do these solution spaces intersect? And I'm just gonna bring the desk down because my back hurts. Okay. It is very important that we notice that there is no guarantee that lines do in fact intersect. Note. And this is where jumping back and forth between algebra and geometry is really useful, because this is a geometric axiom in one of Euclid's axioms, I think, she says. Lines may not intersect. E.g., parallel lines. By definition, they never touch. So there are no solutions. Okay, and that might be y equals x plus 1 and y equals x plus 2. There are no values that I can plug into both of those equations that will solve both of them. Euclid's axiom is that lines either intersect or are parallel. Thank you. Okay. However, if lines are not parallel, they will intersect exactly once. And I'm really hoping that a keen bean is going to be like, Kat, what about the secret third option? And we're going to get there. So even if lines look really, really, I'm going to get the straight line tool out for this because I'm going to mess it up. If lines look really, really parallel, okay. Why is the snapping function ruining this for me? I don't know why that is not letting me do what I want to do. Pretend those are two straight lines. They will at some point touch, basically, is what I'm trying to get to. So they look nearly parallel over here, and then they do eventually. Okay, I think that end of my Wacom pad is just being a bit weird. So all lines will touch exactly once. Now, what about two lines that are on top of each other? They have infinitely many solutions. So if, oh my god, stop it. overlap. They touch everywhere. And the system has infinitely many solutions. And a good example of this would be x plus y equals 2 and 2x plus 2y equals 4. And you're like, Kat, those are the same equations. And I'm like, no, 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 they're not. They're different. One is twice the other. If I were to draw it as a vector, it's the same, but scaled. What about the third option? Yeah, so system of equations. Yeah, in 2D has 0, 1, or infinitely many solutions. Okay, if we get 2, we done fucked up. Basically, is where we're happening. And every time I do this, I'm like, am I allowed to swear on YouTube? Because these VODs just go up as is, and but yeah, that's what we're happening. And then this one and this one are like parallel, and then parallel with fewer steps. One is intersect. I think I have to specify R2 because you can get like two planes in 3D will intersect along a series of line of points. Lines in 3D can be skew. Yeah. Okay. So that's some rules about a system of equations. So we can solve equations and we could go about doing it. So as a little recap. So when learning simultaneous equations, the rules are that we number the equations, set the coefficients, or try and eliminate one variable. Rather than just set the coefficient to 0. So we can add multiples of one equation to the other. We can multiply equations by scalars, and we can swap equations around. Well, we don't really need that one. So that's what we can do in simultaneous equations, and then substitute found variable into equation to obtain the other. Okay, so those are the rules for simultaneous equations, and we're going to do a worked example now. So I'm going to use the same example from before. So we had 2y plus 3x is 4, and x minus y equals 7. So label them 1 and 2. And then what I'm going to do is I'm going to do equation 1, add 2 lots of equation 2. So when I do this, I do it variable wise. So firstly, I'm just going to rearrange equation 2 to swap them around. So this is actually minus y add x is 7, just so I can do top down. So I take equation 1 and I do 2y plus 3x on the left-hand side, minus 2 lots of the left-hand side of equation 2, so minus y plus x, I suppose I didn't really need to do that, is on this side 4 plus 2 lots of the right-hand side, 7. Okay, so I've taken this bit and plonked it there, and that bit, whew, and plonked it there, multiplied, added both sides by 2, instantly in with the wrong sign there. Okay, solving this then, we get 2y plus 3x minus 2y plus 2x is 4 plus 14. So we get these cancel out, which is what we wanted. So we have 5x is 18. So x is 18 over 5. And then we substitute this value in. So I'm going to sub it into equation 2 just so I don't have to multiply it by anything. So we get minus y plus 18 over 5 is equals to 7. And that means that 18 over 5, it's like I'm trying to do it wrong. 18 over 5 minus 7 is equals to y. And that's a value I don't want to do in my head. 18 over 5 minus 7. Y is minus 17 over 5. And that gives us our coordinate pair, 18 over 5 minus 17 over 5, is the solution to both of these equations. And we can check our work over here by doing 2y plus 3x equals 4. And we're not going to extend it to 3D, I just want to look in 2D. So this is my x coordinate, my y coordinate. And I'll do another one, which is x minus y equals 7. So there's our two lines. We can see that they intersect, and we can check what point that is in space. It's not going to let me click on it. So in that case, let me just put in here 18 over 5 minus 17 over 5. And that plonks it in as a plot, as a dot, which is where they intersect. So we can check our solutions by just plotting it, or plugging both of the coordinate pairs into both equations to see if it is on both of those lines. So that's solving simultaneous equations normally. We want to do linear algebra, we want to get more complicated. So we're going to make it a bit more interesting for ourselves. So, I'm going to tell you that we can write a system of linear equations as a matrix vector equation. Okay? Specifically of the form, and this is where this equation is ridiculously famous. AX equals B. So, we have contained in this our matrix of coefficients, our vector of variables, and our vector of constants. Okay? Don't need to remember all that. We'll do a demo of y now. If we go back to our equation that we had before, we had 3x plus 2y is 4, and x minus y is 7. I think I've got those the right way around. 2y plus 3x is 3x plus 2y, yeah. So I've written them intentionally in an x plus y thing. If the vector x is xy, then if I were to do this matrix multiplication, what do I get? I get coming across the top and down. So remember, when we do matrix multiplication, we go across the first row and down the first column, and then across the first row down the second column, and so on, and then we go down. And we do the second row, first column, second row, second column, and so on and so forth. So here we have 3x plus 2y in that one, and then we run out of columns, so we don't have a second entry here. And then if we do it this one in this way, we have 1x minus 1y. Okay, which I'm now reading the rows as my two left-hand side of my equation. So left-hand side of equation 1, and this entry is left-hand side of equation 2. So the equation 3, 2, 1 minus 1 xy equals 4, 7. I can read this row by row as the different equations up here. Whereby doing this matrix multiplication would give me 3x plus 2y, x minus y is 4, 7. I've just written out in columns, so each row corresponds to an equation. So this isn't just a cool way to write them, although it is that, because it's quite nice, especially when you start getting more complicated systems of equations that you want to work with. There is a really useful way to solve this as well. So we can use this notation to help solve, learn about complex systems. Of equations. By that I mean if we start having 5 or 6 equations or loads of variables, that sort of stuff. So if I had the equation 6x is 12, we'd easily solve it by dividing both sides by 6. And that would look something like 1 over 6 times 6x is 1 over 6 times 12. And the 6's would cancel out here, and we get x is 12 over 6, which is equals to 2. But equivalently, we could, instead of writing 1 over 6, we could do x is 12 times 6 to the minus 1 equals 2. Because division is our inverse operator for multiplication. So that -1 means 1 over when we're talking about numbers. So we have that. So my question is, can we do the same thing with the matrices? So we have AX equals B. Can we just do X is A inverse B? And the answer is yes, but not yet, basically. So we'd have to not only know what an inverse matrix is, how to calculate it, but if it even exists. Is how to compute and if it exists. In the same way we can't divide by 0, we can't divide by a matrix that doesn't exist, we can't multiply it by an inverse matrix that isn't there. So this will be covered next time. Haha, look at me leaving cliffhangers. Now I'm not finishing there, this isn't just like a very, very short lecture stream. We do have more, we have another way of working this out, which I would think is a nice way to get comfortable playing around with matrices first, rather than going through this route of inverses. And I thought really long and hard about whether or not that was possible. But yeah, the long and short of it will be that we're looking for an inverse matrix, which is the one that we multiply together to get the identity. Now that I will cover again in the future, in next week's lecture, but hopefully you remember from last week that we did the identity matrix, which was this like leading ones. So ones on the main diagonal and zeros everywhere else. That's our identity matrix. And that was just when we multiply something by its identity by the identity matrix, we get the same matrix back. I will touch on that because that is going to be useful. But can also motivate the definition of this is by looking at the result of Gaussian elimination. Yeah. So there is an operator that exists, and this is the same as when we were doing vector or like scalar multiplication. You multiply something by its inverse, you get out an identity. It's the same sort of thing happening. So yeah, we will touch on that approach next time. But for now, we're back to solving our system of equations. So okay. So if I were to do this matrix multiplication, essentially what we're doing is we're looking for a vector C such that the identity matrix times X is equals to C. Now, if we were going to do the other way of doing it, then we would say that this is A inverse B, but we're not doing that way, so stop talking about it. But that's what we're looking for. If we have this matrix equation with A and X and B, we want to do something to this system of equations so that we get the matrix C, because that will be equal to X. So we'll start from the process. So rather than worrying about X, the reason that we write it in this matrix form is to sort of make it nice and neat. And I think this is where it's called the augmented matrix. which is essentially the matrix A, B. I think that's right, and I am going to check myself. Yes. Okay. And here, this like line is just an artifact so that I know what I'm doing, but it's called a partition. So we can write a matrix as like a subset of different partitions, but the overall matrix will have some form. So in the case that we had before, AX equals B was 2, 3, 1, 3, 2, 1, minus 1. X, Y is 4, 7. Our augmented matrix is going to be 3, 2, 1, minus 1, big line, 4, 7. And I'm pretty sure this is just so that you can, like, the line is there so we can see what's the solution and what's the coefficients. But generally speaking, if this is an n by m matrix and this is going to be an n by 1, this is an n plus 1, n by m plus 1. Okay, you just add an extra column on. Is that right? Yes, but I've done my m and my n the wrong way around. L, M, N. Sorry, I am going to change that because that is actually upsetting me. So here this was a 2 by 2, and this was a 2 by 1, and now this is a 2 by 3. Okay? So this is our augmented matrix. And then essentially we're going to do a procedure to this matrix that will give us something that looks like 1, 0, 0, 1, C1, C2, where this is then our solution. So what do we do in the middle? It's called Gauss-Jordan elimination. We just start eliminating all of these old men that are in the way. Yeah, no, it's. I think there's a Gaussian elimination and then there's Gauss-Jordan, and getting all the way through is Gauss-Jordan. Don't tempt me. Okay. So that's your spoiler. This is what we're going to do. I'm going to teach you how to get from this to this as soon as I go and Google the answer. No, I'm going to go look up another form, another equation for a demo, because I want to do a bigger one. I'm going to do a 3 by 3 because I don't suffer enough. So we're going to have a quick break, and then I will be back very shortly. So stick around. I'll be about just under 5 minutes. But yeah, I've been going for a long time today, so see you soon. Hello. Okay. I have an example. I have 2 examples. It's very exciting. So before we get into that, we need some definitions. So remember, we're looking for how to get a matrix, an augmented matrix, which we've gotten from a system of equations, into a form that has this like I times C, or like near enough, something. We don't really care about the coefficients, to be honest, but we kind of need them to be zeros if or ones if that would be nice, and then some coefficients on the other side. So some terminology about matrices. A matrix is in echelon form when. So essentially what we're saying is we want the right-hand side of this augmented matrix to be in echelon form. But we have to know what that means first. The number of zeros before the leading non-zero term which is the leftmost non-zero term, increases row-wise till only 0 rows remain. A bit complicated. Essentially what that means is that in a row, the leftmost column, the leftmost non-zero entry has obviously zeros in front of it, and then zeros beneath it as well. So some examples of this are this, like 1, 2, 3, 0, 0, 4. That's in row echelon form, because if we go row-wise, and so left to right, top to bottom, the leading non-zero here is this 1, and then the leading non-zero here is 4. So the left and down of the leading non-zero entry is 0. Equally, we could have something like 1, 0, 1, 0, 1, 0, 0, 0, 0. Okay, this is in row echelon form because everything to the left and down of our leading ones is 0. 1, 2, 3, 0, 0, 0, 0, 0, 1. This is not in row echelon form because of this row here. I am pretty sure. Row does not contain entirely zeros. The first non-zero number in the row is a 1. If there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Yeah, so that is not in row echelon form. And then also, any two successive rows that do not consist entirely of zeros, the leading one in the lower row occurs farther to the right than the leading row in the higher thing. So equally, 0, 1, 0, 1, 0, 0, 0, 0, 0. This is not, because the first row is to the right of the second row in the terms of the leading non-zeros. Okay? If a column, even, containing a leading non-zero I think it's not only leading non-zero, it's leading 1, right? I just had that page. Sorry. Is a 1 and increases row-wise. So up here we have 2, 0, 1, 0, 1, 0. This is not in row echelon form because that has to be a 1. So if a column containing a leading 1 has zeros every other entry, then it is in reduced row echelon form. And I probably should have said up here as well, this is row echelon form. We could impose the same restrictions in columns and then solve everything in terms of columns, but like we're not going to do that, so it's row echelon form. So, the identity matrix is in reduced row echelon form. 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. Beautiful. Row echelon form. Every column that contains a leading one has zeros everywhere else. Equally, 1, 0, 2, 0, 0, 1, 0, 0, 0, 0, 0, 1. That is also in reduced row echelon form because this column doesn't contain a leading one, so it's allowed to have a 2 in it. But the others, the first, second, and fourth columns, have to have zeros everywhere aside from the leading ones. If it had something here, if this was also a value of 1, then this would now be in row echelon form, not reduced row echelon form. So when we talk about remembering our motivation, we're trying to get our left-hand side in a form, into some form that lets us do something with our variables and solve our system of equations. What we want to do is get it in reduced row echelon form. So to solve the system AX equals B, we want to get the left-hand side of the augmented matrix in reduced echelon form. Now, we could get it in row echelon form, and that would give us a simpler system of linear equations to solve. And sometimes we can't actually get it in row echelon form, and that will come up in reduced row echelon form, and that might come up in a bit. But the ultimate goal for Gauss-Jordan elimination is get it into that reduced row echelon form. And that will be nice. That'll be good. So let's do that. So finally, we're going to solve our equations again. So we have 3x plus 2y equals 4, and x minus y is 7 using Gauss-Jordan elimination. This was the thing in my first year of undergrad that really wound me up, actually, in exams, because there would be like, solve this using Gaussian elimination, solve this using Gauss-Jordan elimination. And like, if you didn't follow through depending on what the question was, and I was like, it's just one word, and I got the solution. But for proof of being able to do it, let's go. So step 1. Write the augmented matrix. Step 2. Use matrix manipulation, which I just realized I haven't actually described. What is it called? Row operations? Yeah. And then step 3, profit. By that I mean read it back Solon's 2 equations. Okay, so we need to know our row operations, of which there are 3. And actually, they're very similar to the things that I said that we could do to matrix equation, to the simultaneous equations before. So the first one is we can multiply a row by a scalar. And the way that we denote these is the row I goes to k ri. So we replace the row with a scaled version of the row, and that's the same as multiplying through an entire equation by a constant. We can add rows together. So that'd be ri goes to ri plus rj, adding 2 different rows together. And then the third one that we don't really ever need to do with solving simultaneous equations normally and algebraically, but we do need for this reduced row echelon form or row echelon form, is we can swap around. So ri swaps with rj. And normally we combine the first 2, just to speed it up. Normally if I'm going to multiply a row by a constant, it's because I then want to add that amount of that new version of the row to something else. So it's a lot easier to just say that ri goes to ai plus b rj. So say I want to times it by 2 and then subtract the other row, I just do that all in one. But the way that we write out what we're doing with these matrices is these arrow equations. So ri goes to kri, and so on and so forth. So let's do it. Starting with our matrix equation. Our augmented matrix is 3, 2, 1 minus 1, 4, 7. Okay. So the way that I want to go about doing this is I want to get my leading ones in the top corners. Remember, my row echelon form has leftmost leading ones. So let's look down this first column and see if we can find a 1, and we can. So in order to get that 1 in the top left corner, I'm going to do R1 swaps with R2. And that'll get me 1 minus 1, 7, 3, 2, 4. Okay, so all I've done is I've swapped the rows, and now I have a leading 1. So in order for that to be a leading 1 properly, everything beneath it needs to be 0. So everything beneath the leading 1 must be 0. So in order to do that, I'm going to subtract. What do I need to do to R2, so my second row, to get rid of that 3? Well, I need to do 3 minus 3 to get 0. So I'll do R2 minus 3 lots of R1. So that looks like this. To write my matrix, so I leave R1 alone. I'm not doing anything to R1. And then it's element-wise. So whatever I do to the top, I go down and I do it to that column. So 3 lots of R1, so I get 3 minus 3 lots of 1 is 1. And then I get 2 minus 3 minus 1. And then I get 4 minus 3 lots of 7. And that is equivalent to 1 minus 1, 7. 3 minus 3 is 0. Now that column is all sorted. 2 minus 3 is 5. 4 minus 21 is minus 17. checking back in with how we're getting with our row echelon form, this column is now done. Okay? We only have one more column to fix. We only care about this left-hand side. So everything before the thing being in reduced row echelon form. I don't really care what happens to this. This is my solution. This is what I'm trying to find. If I knew what I wanted to happen to it, it would be gone. So I now look for my next leftmost entry, which is this one. And I want that to be 1. I want it to be a leading 1. So what I need to do to this row is divide by 5. So I do R2 goes to 1 over 5 R2. And that gets me the matrix 1 minus 1, 7, 0, 5 divided by 5 is 1, and minus 17 over 5. Okay. So now I have my leading 1, and I have my leading 1, and everything to the left and down is a 0. So this left-hand side is now in row echelon form. If we were only doing, we were only doing Gaussian elimination, we would stop here as we're done. Solving this then involves putting it back in. So you get x minus y equals 7, and you get y is minus 17 over 5. X minus 17 over 5 is 7. X is 18 over 5. So that's row echelon, and you'd be done, and then you'd solve it. But that's not helpful, I think, especially when we have the ability to solve it properly, and then we can just immediately read off the right-hand side of this augmented matrix. So we're going to do a few more steps to get it down to, so 1 minus 1, 0, 1, 7, minus 17 over 5. Okay, and all we're going to do is R1 goes to R1 add R2. And that looks like 1 add 0, minus 1 add 1. Leave this row alone. 7 minus 17 over 5. Because that then puts it in the form 1, 0, 0, 1, 18 over 5 minus 17 over 5. Okay, which is precisely the identity matrix and some vector c, where x is equals to c. So x, xy, which is our matrix x, is 18 over 5 minus 17 over 5, or equivalently reading it, x is 18 over 5, y is minus 17 over 5. So that is solving it with Gauss-Jordan. So taking it from what is row echelon form, where you just have the leading ones and everything left and down, to reduced row echelon form, where not only do you have that, but you also have things above it being 0 as well. Takes it through to the full solution. So we can do that again, but for more complicated matrices. Solve the system. x plus 2y plus 3z is 5. 2x plus 5y plus 3z is 3. X plus 8z is 17. Okay, so augmented matrix. So here we have to be a little bit careful because we do have a 0 in it as well. So reading off of the coefficients, we get 1, 2, 3, line 5. We get 2, 5, 3, 3, and then we get 1, 0, 8, 17. So that's our augmented matrix. So going through the steps again, we want to get the left-hand side of this, which is now a 3 by 3 matrix, into reduced row echelon form. So finding the leading one to start, we already have one, so that's okay. So now we just need to make everything beneath it 0. So we'll do R3 goes to R3. Do I want to do that first? Actually, let's do R2 first. So we'll work down procedurally. So R2 goes to R2 minus 2 R1, and that'll get rid of that 2 underneath it. So leaving everything else alone in this matrix, 5 and 1, 0, 8, 17. So 2 minus 2 is 0. 5 minus 2 lots of 2 is 1, so 5 minus 4 is 1. And then 3 minus 2 lots of 3 is minus 3. 3 minus 2 lots of 5 is minus 7. Okay, so second row done. Now we need to get rid of the final entry, so the 1, 3 entry. So we do R3 goes to R3 minus R1. So we only need to do one lot of it, which should be quite nice. So again, leaving everything alone that we're not currently touching. So we should be able to just write out 2 rows, maybe minus 7. And this is where like first year undergrads get bored and just start like, I'm just going to do 17 operations in one go. And by undergrads in first year, I meant me in first year. I was that kid. So 0 minus 2 is minus 2. 8 minus 3 is 5. 17 minus 5 is 12. Right. Then we find the leading ones. So we've left that one all right. That's okay. The next leading one is actually already done for us, so that's stunning. So now we just need to get rid of everything beneath it. So we want to get rid of that minus 2. So we do row 3 becomes row 3 minus, add 2 lots of row 2. And doing it in this way, left to right and top to bottom, means that you're never accidentally adding back an extra row, because what you could see is here, if I'm like, oh, I need to add 2 to this, there's a 2 there, so I'll add row 1 to row 3, but then I end up with a 1 here, and then I lose my sort of row echelon-ness that I've already found. So we don't want to do that. So we, again, leave the rows alone that we're not playing with at the minute. Okay, so 0, add 2 lots of 0 is still 0. Minus 2, add 2 lots of 2 is, 2 lots of 1 is 0. 5, add 2 lots of minus 3. So 5 minus 6 is minus 1. And then 12 minus 2 lots of 12 add 2 lots of minus 7, so you get minus 14, so you end up with minus 2. Okay, now we need to find a leading one, so it's not there yet, it's currently minus 1. So the only thing that's left to do is R3 goes to minus R3. And now we should have 1, 2, 3, again leaving alone the rows that we're not dealing with at the minute. 0, 0, 1, 2. So we multiply both of those by minus and they become positive, which is fantastic. So now we have our leading ones and everything to the left and to the bottom of them is zeros. So this is in row echelon form. Working reduced row echelon. Reduced row echelon, we work backwards. So starting from the furthest right leading thing, get rid of everything above it. So we'll work upwards. So R2 goes to R2, add 3, R3. 1, 2, 3, 5, 0, 0, 1, 2. So that gets left alone. So minus 3 add 3 is 0. Minus 7 add 6 is minus 1. And that row's done. Cool. Now we need to do 2 more operations to row 1. So again, we'll stay in that leftmost column, rightmost column, and we'll do R1 goes to R1 plus minus 3 R3. Zero, 0, 1. It's very weird writing a matrix from the bottom, but we're not touching the bottom 2 rows, so it makes sense to do. Okay, 1 minus 3 times 0 is 1, 2 minus 3 times 2 is 2, 3 minus 3 is 0, 5 minus 3 times 2, so we get 5 minus 6, so you get minus 1. Yes. Okay. Then we need to get rid of that 2, and that's the only thing left. So we do R1 goes to R1, and we need to subtract 2 lots of R2 from it. So 0, 1, 0, 0, 0, 1, minus 1, 2. One more. Okay, leave the 1 alone. Yeah, that gets left alone as well because it's a 0. So 2 is 0. So we now have that in the identity matrix. That's really useful. Minus 1. This is where I have like too many minuses. 2 minus 1. So you have minus 1, add 2. Okay, that is 1. This is where scrap paper comes in really, really handy. So that tells me if I then plug this back in, what I get is 1, 0, 0, 0, 1, 0, 0, 0, 1. X, Y, Z is equals to 1 minus 1, 2. But solving this out, you get X is 1, Y is minus 1, and Z is 2. So that is reduced row echelon form. So this is all the way down to Gauss-Jordan. Elimination for that. You don't have to do it left to right, top to bottom, but it is a lot easier because you end up going back on yourself quite a lot. So the only thing that we haven't touched on is what happens when you can't actually get it all the way down to an identity matrix. And that is still solvable, sort of. Now, is there a nice way to do this? Okay. So say we have a system of equations that we eventually get down. So what if we can't? So say we get down and we have something that looks like this, and we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 3, somehow we've ended up with this in a 3D system. And what that would tell me is that x is 3, y is 2, and z can be anything. It's undefined. Equally, we could end up with something where this is like 1, 1, 0. And we end up with I think that's technically z is 2. Yeah, it's underspecified. So if we solve this system of equations, we'd get x plus y is equals to 3, and z is equals to 2. And basically what we'd have to do is we'd have to set y as some parameter s, and then our system of equations is determined in terms of s. But we will focus more on what we do in this situation next week. And also we'll be able to tell, before we do this really long Gauss-Jordan elimination process and we're getting it into reducer echelon form, we'll be able to tell, like, if we even can find a set of solutions that is nice. As well as more geometric, okay, what does this mean? Remember, if we have in 1D or in 2D these parallel lines, or these lines that don't touch, what does that look like in higher dimensions, and what does it mean for your system of equations in higher dimensions? So as a very brief summary, we've looked at reintroducing what a linear equation is. We've been looking a lot at starting with really simple and geometric interpretations, linear equations in 2 dimensions of straight lines, straight planes. They're typically like the space of the lower dimensional shape. And we disregarded anything higher powered. So it's anything with a linear variable and a constant coefficient. We talked about intersections. So the intersection of 2 straight lines is either at a single point, infinitely many points in the space, or not at all. So they can only touch once, 0, 1, or infinitely many times, which is a nice check. If you end up with 2, you've done something wrong. You've been able to write systems of equations as matrix equations. So when we solve simultaneous equations, we do a series of operations to these equations, and we do something very similar called row operations in matrices. So we write systems of linear equations as ax equals b, where a is our matrix of coefficients, x is our equation of a vector of variables, and b is our vector of constant terms. And this is the iconic matrix equation. This is the thing. If you can solve these really fast, really well, you're doing all right. This is why I love MATLAB, is because MATLAB as a solver was written specifically to solve matrix equations. It does matrix equations really fast because it was designed by mathematicians, and we use matrix equations a lot. But generally speaking, you write them in what's called an augmented form, and you solve them. And you can solve them just by computing the inverse matrix of A, which sort of undoes or divides by A, and multiplying by the left-hand side by that. But if you can't do that, there are procedures, and there's this algorithm, either Gaussian elimination or Gauss-Jordan elimination, that we can use. So we skipped over inverse matrices and started looking at Gaussian elimination. So in order to do that, we write the augmented matrix, which is taking our coefficients and taking our constants and then smushing them both together inside of a matrix with a partition, which is this line dividing them down. And then performing a series of operations on the right-hand side of the equation of the matrix, which does it to all of the matrix, but trying to get the right-hand side of the matrix in reduced row echelon form or row echelon form. Row echelon form being the leftmost non-zero entry on a row is a 1, and that 1 is preceded by zeros and has zeros beneath it. And if it is in reduced row echelon form, there are zeros the entire column, so above and below. Solving a system of equations then, write it in its augmented matrix, perform a series of row operations, which are multiplying rows, adding and subtracting rows, and swapping rows, to get it in reduced row echelon form, and then read off your system of solutions, of which there should be a single one. And then we did that for a 2D example, and we did it for a 3D example. And I'm pretty sure both of those answers are right. So that's where we're going to leave it for this week. Next week, as I say, we'll be doing some more complicated stuff with looking at matrices, including their inverses, their determinants, as well as like ranks of systems of equations. So this is the long-winded sort of by hand method, and now we're going to sort of skip ahead to a faster method for solving systems of equations. Well, faster depending if you're a computer.